Hello everyone. In this video, we're going to begin lesson 3, which is association between variables. So in lesson 2, we talked about looking at one variable at a time, both quantitative and categorical variables, and we saw what we could do in describing them and graphing them. Here we're going to do the same thing, but for looking at multiple variables together. Okay, so what if we view them together? Are there any relationships that can be found? This turns out to be where a lot of people are interested in, and where a lot of the interesting questions come. So for instance, an old question was, are smoking and lung cancer related in some way? Okay, does smoking cause lung cancer? Or maybe just, is there a relationship between smoking and lung cancer? That means we're looking at both of the variables together and how they relate to each other. So we started this really at the end of lesson 2. I gave two different graphs or two different plots on how we could use box plots and histograms to view multiple groups together. And so here we have that second picture that I showed with box plots, and we have one categorical variable, clarity, and then I'm graphing on the y-axis a quantitative variable, the price of the diamonds. These are about, this is from the diamonds data set. And so when we have one categorical and one quantitative variable, there's sort of limited stuff that we can do there. The book does talk about what you can do, but I'm going to skip over that, and I'm going to move to the first thing, which is the first thing that we'll talk about, two categorical variables together. Now, before I do that, I have to introduce some terms that we'll use throughout this lesson and even after this lesson. So these terms will be kind of used throughout the course, and as you'll notice probably so far, this course is filled with terms. I said at the beginning, and I'll say it again, that this course is going to be different than any math course that you've taken so far, and it's going to be like learning a new language. Statistics is like a new language. Some people have said that statistics is the language of science, and so that's a pretty broad statement, and I won't go as far as making that as well, but a lot of people have said that. Okay, so anyway, I'm sorry for my rant. I do that from time to time. So when we look at two variables at once, there's going to be one variable that's sort of what I'm going to call the explanatory variable, and the other is the response variable. So the explanatory variable is what I'm often going to say or call the x variable. So as a definition, we're looking to explain the behavior in the response with the explanatory variable. So in the example with smoking and lung cancer, I would say that smoking is the explanatory variable, and we're looking to see if you smoke or not makes a difference in your likelihood of getting lung cancer sometime in your life. Okay, so the explanatory variable is looking to explain the behavior in the response, and then of course the response is the outcome variable. I'll often call it the y variable. So it's the outcome variable on which comparisons are made for different values of the explanatory variable. Okay, so it's the response. The explanatory will be on the x, the response will be on the y-axis, oftentimes when I make plots on the xy axis that we're used to. So, and the other term that really we focus on in this lesson is association. And so when I talk about association, I mean this, okay? An association is, this is a bad definition because I'm using the word in the definition. I'm sorry for that. An association between two variables, and I'm using the wrong two there as well. Please forgive me. I should have proofread this better. An association between two variables exists if particular values of one variable are more likely to occur with certain values of the other variable. Okay, so that's a bit of a long-winded definition. What I mean is that if you see that, especially with quantitative variables, if x increases and then y increases with it, then there's an association. In my lung cancer, smoking and lung cancer example, if I surveyed 50 smokers and 45 of them got lung cancer, and then if I also surveyed 50 non-smokers and only 5 of them got lung cancer, there certainly seems like there's something there. Okay, a lot more. If we can talk about proportions, which we focused on in lesson 2, the proportion of people who smoked and had lung cancer is much larger than the people who didn't smoke and got lung cancer. Okay, so that's association. Now, to get to where what I was talking about before, if I have 2 categorical variables, okay, I can view them together, okay, and when I view them together, I'm going to view them in what's called a contingency table. Okay, so in lesson 1, we talked about frequency tables. That's looking at one categorical variable by itself. When I view 2 of them together, it's called a contingency table. So I'll go back. A contingency table cross-tabulates the occurrences of each variable in conjunction. So I'm sure that makes it not very clear at all what a contingency table is, but I'll show you what one looks like. And what I'll use is an example that I used in lesson 1, okay, on gender and handedness. Okay, so and also I apologize that there's only male and female in this data set. It's just not large enough. There were no non-binary options. Okay, so or no binary people, non-binary people who answered this. Anyway, I have my elongated data set, which you made frequency tables of. Okay, a contingency table is going to count the number of occurrences that I see of each variable together. Okay, so for instance, the first observation in my data set was a male who was right-handed. So I'm going to go through this data set and look for all the people who were male and right-handed. So here's 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so I do that, and then I do that for all possible combinations. So here I only have 4 possible answers: male right, male left, female right, and female left. Okay, and so when I count all them up, I put them in a table. Okay, and so you'll read the table as I look to this row. I look for the rows for gender, the columns for handedness. And so this 8 here represents all males who were right-handed. And so we counted that before and found there was 8 of them. So there we go. All right. And so we can use this contingency table to calculate proportions like we did before in lesson 1. Okay, so let's do that. So there's my contingency table that I found in the last problem. And I can talk about different proportions within this contingency table. The first type of proportion that I want to talk about is called a marginal proportion. Okay? And it is the proportion of the whole for a particular category of one of the variables. So for instance, if I asked you to find the proportion of respondents who were male, okay, I would have to count up all of the people in the data set, okay? And so there are 8, 8, 3, and 1. When you add them all together, you get 20, okay? And then I have to find how many males there were, okay? And so how many males were there? There were 8 males who were right-handed and 3 males who were left-handed. So I have to add across this row to get 11 and then divide by 20. 11 out of 20 is 0.55. Okay, so that's the proportion, 0.55. If I wanted to change that to a percent, I could say 55%. Okay. The second type of proportion that's a little bit trickier, okay, but actually is used to give stronger statements. So it's more powerful and yet more tricky, okay, as most things are in the world. A conditional proportion is the proportion of a category of one variable given the value of another variable. Okay, so that given part is very important. So here's a question that you would see for a conditional proportion. So I want to find the proportion of people who are male given that they're already right-handed. Okay, so given that you're right-handed, what's the probability or what's the proportion of males there were? Okay, and so when I ask a conditional proportion question, I'm going to change the denominator in my division problem. So I'm no longer looking at all of the people. I'm only looking at the people who are right-handed. And I get that from my given statement. So I already know that this person is right-handed. What's the probability that they were male? So if you have a hard time thinking about this type of question, you can believe or think of a scenario where I am, where you are on a game show, okay? So you're on like The Price is Right or something. And the game show is that somebody walks up behind this black screen that you cannot see, and I'm going to ask you, based on the data that you have, maybe this contingency table, what's the probability that this person is male? And you would say, well, it's 11 out of 20. Okay, this conditional proportion is going to say, instead of just asking what's the probability that the person behind the screen is male, they're going to give you some extra information. They're going to say, all right, they're going to say that this person is right-handed. Given that information, then what's the proportion? What's the probability that the person is male? I know this is a really lame game show, but it's an example nonetheless. Okay, so I have to look and say, well, how many people in the data set are right-handed? And so you see there were 8 males and 8 females, so there are 16 total. And so what's the proportion of those people who were right-handed that were male? And so you'll see it's 8 out of 16, or 0.5 is the proportion. 50% would be the percent, okay? And I'd say that the probability of that happening is 0.5, okay? Or 50%. So that is marginal and conditional proportions. I will expect you to calculate these for a given contingency table. So for the reading assignment for this first little part on contingency tables and categorical variable type stuff, you can read pages 93 through 98. Okay, I do really suggest that you do read these assignments, that you can gain extra insight that I just don't have time to put in these videos. And then where I'll stop is that I'll give you a year turn. All right, and so in this year turn, I have a contingency table here on hair and eye color. So you'll see hair color is on the row. Okay, so hair color, black, brown, red, and blonde. And then eye color, brown, blue, hazel, and green. And so I ask you to find 3 proportions. And so you'll see that the first 2 are marginal proportions, and then the third is a conditional proportion. All right, so that's where I'll stop for this video. I'll see you next time.